Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I would say just start. Today I'm going to talk about secure, trusted overlay networks for robust privacy, protecting communication. That's basically about my PhD thesis work at Princeton University. So first of all, I want to explain what the issues are with anonymous communication. So we basically have three parties, Alice, Bob, and Eve. And so the first aspect is basically the sender-receiver anonymity, so each other's identity from another, and the second one would be the unlinkability. So Eve, as a third party, should not learn that actually Alice and Bob are communicating. The third aspect of anonymous communication is also location independence. So the network position for Alice and Bob should not be clear to any of the three parties. Those are basically the goals that we want to achieve to make a system really secure and robust for privacy. So problem number one in this whole work is the traffic analysis. So if this one computer communicates with the other computer, actually everybody could see the path through the network. Secondly, we could actually measure this end delay of the packets to the end between the two ends. And the network could have a global or partial adversary, so the adversary could control a large number of nodes or just a small number of nodes. And typical traffic analysis methods would be like timing analysis. You would just measure the inter-packet time or just count the number of packets that go through these intermediate nodes. The second problem we face in this whole area is software bugs. So somebody could recruit a large botnet and basically start monitoring traffic, and he becomes a much more powerful adversary than it used to be before. And so these problems are related to software bugs, where bad software makes it possible for an adversary to compromise a large number of nodes and to get more powerful traffic analysis. So basically infects these PCs and recruits them as botnets. We accumulate these botnets in the anonymity network and raise the number of nodes for traffic analysis. And additional protection against software bugs also makes the system more robust against traffic analysis. So to face these two issues, I have set up this talk by first looking at how we can use trusted computing to do that. The second one would be how to do when we talk about traffic analysis, so what are the various traffic analysis attacks and how to protect against them. Then I talk about the design of Stone, and last I present the results. So the first thing, or the most common thing in traffic analysis protection are mixed networks. So a mixed network is basically a collection of nodes. And so all messages go through all of these nodes. It's basically a cascade. So there are basically messages over here, and they go through all these stages of the mixes, and every mix shuffles these messages in a random order and sends them out again. And the first, basically every sender has to encrypt in layers, as shown here, with these public keys of the various mixes before they actually get inserted into the network. And then every node just strips off a layer, shuffles the messages, strips off the next layer, and so on. So we get some kind of a random order of the messages here, but all these intermediate nodes don't know what the order is, because they don't know what the plaintext message is, nor do they know where the nodes come from and where they go to. So the problem is, this is actually prone to software bugs. So if an adversary controls several of these mixes, he would actually learn how these messages get distributed. So he could correlate things like message size or timing. Then scalability and resilience are difficult. So if one of these mixes fails, we need to reorganize the whole mix network to basically do the cascade just without this one node. And every node who is sending has to know all the public keys in advance. Then there's an additional latency for shuffling on every mix, because every mix has to get a certain number of messages until it makes sense to protect against traffic analysis. And if there's only one message traveling through the whole mix network, it's basically useless. And the last one is there's no receiver anonymity. So the sender has to know who is sending to, so he has to know all the public keys along the path. So Alice always knows who Bob is in this mix network. So coming to trusted computing, there are several ideas on how we can actually use trusted computing to improve the situation. So we have this thing between untrusted processes and trusted processes, and this is basically the architecture how I assume trusted computing is going to be. There's a small trusted kernel that can be easily verified, and there's an untrusted kernel that sits on top of the trusted kernel. So these two trusted processes are basically isolated from these untrusted processes. And the idea is that if an adversary compromises one of these untrusted processes, he cannot infect one of these trusted processes that would be used for the network routing. So, and the second advantage is because we have remote attestation, so we can make sure that every node runs the same version of the software. And we can induce some kind of a fail-stop semantics as compared to a Byzantine semantics. So either we know all the vulnerabilities, that means we can assume that the nodes either crash or they work, but there's no real malicious behavior. And that's one of the main advantages, because the malicious behavior would induce that the node could actually monitor traffic arbitrarily. So just to give a quick comparison of fail-stop versus Byzantine semantics. In Byzantine semantics, we have traitors in the system. There's any kind of malicious software possible, like viruses and worms. It's actually very difficult to detect asynchronously, because this simply we don't know whether a node actually hangs or whether it's sending messages. So there are various protocols in the literature that try to solve this problem, but they're all not very good in performance. With fail-stop semantics, this typically a fail-stop processors. We simply restart the system, and it does actually no harm to the system. It only crashes and then restarts. So in terms of, also I should probably add, in terms of a botnet, if we had only fail-stop semantics, it would not be possible to recruit a whole botnet of nodes as compared to Byzantine semantics. So the trusted overlay network, we want to authenticate anonymously to a peer node. All the authenticated nodes basically run the same software. These authenticated nodes have to have some common shared secret, because otherwise anybody could join the network and potentially monitor the traffic. Then we use the fail-stop model instead of the Byzantine model, and it protects against compromises from these botnets because of the failed stop model. So basically what we get at the end is a whole network that just have trusted computing bases on them, and all these nodes authenticate to each other, or not necessarily to each other, depending on the network topology. So now we come to secure and trusted overlay networks. So one thing is we want to protect against traffic analysis. That's the main goal of the work. There's the one issue is that it has to be scalable. It has to be a large anonymous crowd. The more nodes we have, the better it is. The easier it is to hide messages. The second is the sender-receiver anonymity, as mentioned earlier. Those are basically the three traffic analysis requirements. So we want to hide the senders and the receivers in the network. We want to hide the connections in the network. And we also want to make the nodes independent of the location in the internet, or the geographical location. And the second part would basically be trust. We do want to have trusted sockets, so application endpoints that are protected from an adversary, and not like sockets that can be compromised as we would have right now. If the socket is basically, if the machine is compromised, and also the socket is compromised. So the applications don't have to deal with these problems anymore. And the other thing is we want to have one-to-one certificates instead of one-to-n certificates. Because if you would publish a VeriSign certificate, then everybody would know that this person is actually Microsoft.com. But that's not what everybody should know, so otherwise the anonymity is compromised. So there should be a certificate that only says Alice only publishes to Bob that she is actually Alice, and not to anybody else. So now we come to all these traffic analysis attacks that Stone has to protect against. So basically the first part is the predecessor attack, it's shown here. That's a very well-known attack in the literature where nodes in the system analyze the predecessor of the messages. And so the whole idea is that the sender is always in the path between the sender and the receiver, but all the other nodes don't have such a high probability of being in the path. So just by analyzing the predecessor of the message, you can deduce that somebody must be the sender. The second one would be the timing analysis. So two different nodes measure inter-packet times, and they can conclude whether they're on the same path with some probability. The third is basically network tomography. So somebody could just measure end-to-end delays in the network from all various nodes that he controls, and then deduce what the individual link latencies are and what the neighbor relations are. And last, there is the intersection attack. So if somebody measures the traffic volume and there's a constrained topology, not a full connected network, then he can induce some relations between the path. And I'm going to explain these in more detail, especially the predecessor attack first. So we have a network where we have limited number of nodes compromised, so 3 in this case. And there is the traffic from the sender to the receiver. In this case, it just selects one path. It's basically a random walk. Then we select another path, and it happens to be on the path with this one compromised node. So this compromised node knows the IP address and the connection ID for this connection between S and R. Then the next one would be the another compromised node, so he would also learn the IP address of the sender, and then we could pick a whole different path, and then so this guy would learn that his predecessor is actually this guy, and then we pick another path, and then this guy would again see this one as a predecessor, but the statistical probability says that this node is actually more likely to see S on the path, because S is the sender and S is always on the path. So he sees this one IP address very often, and therefore he can deduce that this one must be either close to the sender or with a high probability be the sender. Okay, so the idea is basically to use trusted computing to protect against this attack, simply because we have strong process isolation and remote attestation, and the network secret, we cannot do any logical packet sniffing on the network. So any adversary would be an untrusted process, wouldn't see incoming IP addresses on this trusted process. The only way to actually do it is to do physical packet sniffing on the network. So you have to control the nodes physically and not through a botnet. The weakness, of course, is that the network secret and the trusted computing base are kind of a single point of failure. So if the trusted computing base gets compromised, which is usually hard to do, then you could actually still monitor all these predecessor IP addresses. And in addition, if the network secret leaks, meaning that you can authenticate to any network, a very powerful adversary could actually just penetrate the network and also do this predecessor attack, so the nodes that he controls physically. So the second point is basically a timing analysis. So if you still have these three compromised nodes, the first node receives a certain timing pattern of packets, and the second node also receives the same timing pattern of packets. Then these two nodes can conclude that they are on the same path. Basically, we use random routing to protect against this timing analysis. And random routing is the Valiant style routing from workstation clusters. So I'm going to explain on the next slide how exactly it works. The only weakness is that it creates lots of out-of-order packets, because packets get different delays through the network, and every packet has to traverse the network twice, basically. So in random routing, as I see on the next slide, every node basically picks a random intermediate node and forwards the message to this random intermediate node, and this random intermediate node forwards the message to the receiver. And then the receiver sends it back via another different intermediate node. In this way, we actually balance the traffic across the network, but since we do this detour via the intermediate node, there's some additional cost, so the packet basically has, in the worst case, traversed the network 2 times. So the third attack is network tomography. Network tomography, we do just pings from between 2 random nodes in the network and then pick a different one. And at the end, we want to know what are these latencies of between the nodes. And so the idea is to conclude properties about the actual network topology. If you know the network topology, then just given any any end-to-end delay. We can, with some probability, predict what the path was to the network. So then, in addition, to actually protect against this attack, we shuffle the network nodes. This actually creates additional latencies on shorter distances, but it solves the network tomography problem. So for example, if you had this normal geographic layout of cities in the internet, basically assign some random address and order to this, according to this random address in the network, so that all the neighbor relations get shuffled. So, and the last traffic analysis attack is basically the intersection attack. In the intersection attack, the problem is that the sender who talks to the receiver despite it's taking different paths to the network, nodes that are closer to the sender in a constrained network topology actually have more traffic on their links as compared to nodes that are somewhere in the middle of the network. And using this attack, we have this problem of unbalanced traffic volumes in this partially connected network, so that any node could determine how close it is actually to the sender or the receiver. And this is important when the network topology is known, especially if the tomography attack would succeed. So the only way Stone can actually protect against this kind of attack, since Stone uses a limited network topology, is to balance the send rate across the network. So every node has to send approximately the same rate, which creates additional cover traffic and slows down the senders on the other hand. So if there's a network, like the red nodes are sending at a higher rate than the yellow nodes, we can actually balance the traffic across the network so that they all get even out. And the synchronization actually also benefits from random routing, because simply every node is an intermediate node in the network. Every node in the network roughly knows what the approximate traffic volume is that goes through the network, and can basically adapt to this rate. So now we come to the Stone design. So how does the overlay look like? If you take a pair of nodes, so this is basically the Stone architecture between these two nodes, and the first component of this architecture would be the Stone proxy. The Stone proxy sets up TCP connections to a different Stone proxy on a different node, and on top it communicates with a router. It basically adds like a firewall between the network and the router, and makes also sure that we do the handshake, the TCP handshake, and the key exchange during initialization. On top of this Stone proxy, we have the router, and the two routers actually attest to another when we do the remote attestation, including the Stone proxy. On top of the router, we have the applications that may actually be trusted or untrusted. They can attest voluntarily or not, but that wouldn't compromise the security of the transport system. So only these apps communicate via Stone sockets to the router. So when we now look at the router, we see that they provide the socket to the application and communicate to the proxy using these Stone connections. And so the whole idea of the Stone routing is to maximize the number of nodes in Stone. So we use a structured overlay to do this. And it solves the problem for scalability for neighbor discovery and also minimize the number of handshakes. So if you would have a full connected network, as lots of these typical anonymity networks are right now, you would have to exchange keys with all neighbors when a new node joins. For example, in Tor, every node has to learn about every other node, so it's basically a static proxy network. But this way, we don't have to rely on a static proxy network, but it can be dynamic, so any node who's participating in the network can also forward traffic. So the weaknesses of this, of course, are that link failures break path, and because it's a constrained network structure. There's also a load imbalance, so one node can have a higher bandwidth than another node, and this node can actually become a bottleneck in the network. So, for example, the structured overlay, in general, we use a hypercube architecture. So if the 0, 1, 1 sends a packet to 1, 0, 0, it actually compares bitwise and sets the bits accordingly to forward this packet to the correct position. So first it looks at the first bit, sets it to 1, then the second bit sets it to 0, and then the third bit. So it always takes log n steps to forward this message. So in Stone we use a random hypercube topology. The Stone address is a 64-bit hash of the trusted computing secret key. So nobody can actually duplicate any node IDs in Stone, which is also a problem. There's this Sybil attack where every peer-to-peer node just gets a new node ID, and if you get lots of node IDs, you can easily compromise the whole network. In addition, the base in the hypercube determines the path length. So if you only have base 4, we would have log 4n path length and routing table size. If basically the base becomes very large, the network would become fully connected, which is the trade-off in this case. It's also different from the standard distributed hash tables, simply because you have to optimize for alternative routes instead of replicas. So it's not like finding an object for a key, but it's finding what is the best route to the network for this receiver. And random routing requires load balancing. So in a normal distributed hash tables, we don't care how long it actually takes to get to the destination. But in random routing, we want to have a short round trip time. And if there's a bottleneck node in between, we need to do something about it. So basically, what Stone does, it uses k virtual addresses for load balancing. So the more higher bandwidth a node has, the more virtual addresses it just gets. And it just has more hypercube addresses available. And these additional hypercube addresses are just the hash of the previous address. So it's like a whole hash chain, and it's easily verifiable that this additional, or this node didn't acquire any illegal addresses. For the routing, we use the longest common prefix because it's a random address and not all the nodes in the hypercube may be available. So we have to route through some gaps, basically. So if this is the node address, and this is the destination address, it basically forwards to slot number 3 because this is the longest common prefix. In addition, we use L entries per slot to improve resilience. So every node has 2 alternatives. If one link is broken, it just sends the packet or the message to the second choice. And actually, given that probabilities in the internet, we can assume that there's an availability between 95 and 100%. So we even increased the number of nodes in Stone significantly. We still, with two choices, we get an almost equivalent path probability or path correctness probability. This is path failure probability as comparable to the internet itself. So this is still fine. So next you want to look at these applications. They basically use Stone sockets, which is a standard library that gets linked to the applications to communicate with these routers. The problem with today's applications are, as we've seen in Internet Explorer these days, is that phishing attacks are common, and web browsers nowadays have precautions or some measures against phishing attacks. So there's website spoofing, and malware gets installed. It even records keyboard inputs, so it's getting nastier and nastier. The second issue is that certificates reveal the identities and destroy anonymity, so we can't also use certificates. Simply if Bob would just have a very signed certificate, why do we do the whole anonymity thing anyway? Because everybody would know that he's Bob. So there has to be some kind of a different choice for certificates, similar to what has been done in email pseudonyms, like the early anonymous email issues, where you would just get, similar to AOL Instant Messenger, you would just get a pseudonym that nobody really knows publicly, but only your friends would know. So the first example applications that we have is like an instant messenger application. The problem with this architecture right now is that there's a centralized instant messenger server, and everybody connects to this instant messenger server. And the interesting thing is that there are lots of counter-anonymous or not really privacy-protecting policies. So if you look at AOL Instant Messenger, they explicitly say they can record any messages that go through this instant messenger, and nobody can actually control what he wants to reveal or what he doesn't want to reveal. So there's basically central certification and central anonymization, and we want to distribute this, because now we have this nice infrastructure with a structured overlay. But how are we going to do this? So that's what I'm going to explain. And the next example is the global file system. So if there's a global file system like SFS, where file access is certified but not anonymous, so people know that they actually access the right server because the public key is contained in the server path. And the other option is basically publish subscribe, so the file access is anonymous but it's not certified, similar to what all these peer-to-peer networks use, or even Freenet. So basically we can use Stone to solve this problem and combine anonymity with certification. So the Stone API basically has Stone sockets, which are similar to TCP UDP sockets, just that the socket addresses are opaque capabilities. So that is the huge random string that doesn't tell the user anything about the application, about the network. Then we have application-specific random strings. So even if you know the random string for one application and for another application, they just don't correlate at all. So we cannot say these two applications are talking to the same server. And secondly, we have to deal with all these problems of out-of-order packets and random routing. So there have to be standard transport protocols over Stone that basically provides flow control and packet reordering. And we don't have to use congestion control, and it would actually not be good in the architecture to use it, since we already have congestion avoidance by using random routing. So if there's really a congestion, there's no way to work around in the network, because it's just exhausted the whole bandwidth of the network. And then the second big component is the trusted name service. So we have to find a way to map these opaque predicates to some name. So if you want to look up, Alice wants to look up Bob, she should get a way to find the opaque capability of Bob. And we use public keys as a certification mechanism, basically, similar to what other approaches like SFS do. Just to explain the scenario of these trusted name services, so we say Alice wants to publish her identity, or basically create some kind of a certificate for Bob. So she registers with a trusted name service, and she says registering chat with the key of Alice, the public key of Alice. Then the trusted name service challenges Alice with this public key. So she sends basically a string that she should encrypt, and she confirms that. So then Bob also does the same thing with his public key, and we get the challenge. And then Alice gets the public key of Bob through some offline channel. And then she uses this public key of Bob to query the name service entry. And then the name server just responds with this capability. And the capability is actually not global, so the trusted name service basically embeds some string into the capability string into the packet, and the local trusted computing system on Alice's side basically encrypts it for her per session. So this is, but this capability cannot be intercepted because it's encrypted over the network. So only the trusted computing system itself then converts it into per session capabilities. And finally, Alice uses this capability to connect to Bob. So instead of using an IP address and a port, it just uses this capability. So to solve these two problems, I've explained basically the instant messenger in this example. So every party registers a public key with a trusted name service, and the peers connect using the Stone sockets. And secondly, we have a trusted global file system where every file has a public key on the trusted name service. And if you want to download this file, basically Alice just gets the public key for the certain file and requests the capability for the file from the name service. And then we download and upload the file using Stone sockets. The problem of the name service, of course, is that it has to be replicated throughout the network. If there's just this one node that carries the name service happens to go down, then the system would be compromised. So that's the only issue. So right now, the whole Stone implementation has about 10,000 lines of C code, and we used PlanetLabs for large-scale experiments. We simulated trusted computing on PlanetLab and used the open SSL crypto library. There's a 2-user space process solution right now. So this is Stone proxy and router that are located in different spaces, and it uses asynchronous I/O and pipes for communication between the processes. And there's a watchdog process just in case one process crashes and has to be restarted. Right now performance has not been optimized simply because PlanetLab doesn't allow to load up any kernel modules, and forwarding messages through user space is incredibly slow. So we basically have to copy every single packet on every hop from kernel space to user space and back into kernel space. Just to get an idea on how this TCP works on PlanetLab, so we have the host OS with Linux, and then there's the Linux vServer, which is the virtual server implementation. And the vServer basically provides a whole Linux OS with root access, but it's limited because it's not a real virtual machine. It's more like a user space emulation. So we cannot really modify the kernel. And so the TCP basically sits on top of the OS right now. And the application sits on top of the TCP. So the TCP basically does the TCP handshake and the key exchange and the remote attestation. And it has to be in that order so that the channel is actually encrypted before the remote attestation takes place. So the baseline performance is just a micro benchmark if you set up 2 machines and forward messages forth and back. So you have different fragment or message sizes. If it's 512, I basically contrast or compare the stone performance to an ICMP ping, or this is an echo server which sits in user space. Then we have the stone without any encryption and stone that is encrypted. So ICMP does for basically every packet size, it has the same, almost the same round trip time because it doesn't have to copy any data between user space and kernel space. So the echo server in the user space already has some increased delay because it has to copy data forth and back. And if you add encryption or stone, it's only a very tiny overhead right now using our 2-process solution. So that's pretty much what we would get. Additionally, we did some measurements in the routing table size with 64 nodes on stone. So the measured versus the expected routing table size, this would be log n, what we would get with some constants, simply because we use 2 virtual addresses per node and we use 2 slots per entry. So we have something like 4 times log n. And yeah, this is the measured routing table size. So it's actually pretty much what we would expect if we hash the addresses. So the next slide would be the distance between the stone nodes. So we have 64 nodes on PlanetLab, and we measure the number of hops between nodes. And in this case, it's basically the peak at 2 nodes. Since the nodes all contain random addresses, there's also a random distance, but the majority actually has only 2 hops. And this is also, if you use random routing, we wouldn't get more than 4 hops in between the 2 nodes, which is still acceptable. Then the last experiment is to measure the round trip times between 2 nodes in a sequence. So we basically do a ping across the whole network and measure the round trip times. And these round trip times are binomially distributed. So depending on how many hops it takes through the network, we get a shorter or a longer round trip time, and random routing pretty much randomizes the whole round trip time. If we would just do a normal ICMP ping, all the round trip times would be on this bottom line basically. And we actually also get, that's what I should add, a pretty high absolute value, just because we still haven't optimized the performance issues with the user space to kernel space copying. So we would probably do much better in the future. We also implemented the synchronous down. Basically 8 nodes on a Linux server, and we have one sender-receiver pair that's sent at a full rate. So we get ramp up to a certain throughput over time, which basically shows how the synchronization succeeds. So the idea is to have all the senders in the network send approximately at the same rate, but they also shouldn't ramp up too quickly, because if that would happen, then the whole system would basically oscillate, and we would increase one send rate, the other one would go down, and the other one would go down too much, and then basically end up in this weird state. So conclusions, basically what we did is we fixed this problem of software bugs. So we have fail stop semantics that would require physical access to compromised nodes. Then we used the structured overlay that improves scalability and resilience. We maximized the nodes for assistance against traffic analysis by using the structured overlay, because we can have lots of nodes and nodes can enter and leave. And it's not a fixed set of nodes that could be compromised. The third point is basically random routing. We have the self-mixing property that hides the linkability between sender and receiver. So the order of the packets is completely random routing. We have the self-timing property that basically means that every node knows how much traffic there has to be in the network, and basically can determine its own send rate. Then synchronization is basically the full protection against the intersection attacks if the adversary happens to know something about the network structure. And even without synchronization, Stone is still more powerful than mixes, because it can protect against timing attacks, and it's also protects against scalability and resilience that would otherwise be a problem. Yep, and that's the talk.
Thank you. I learned a lot. I thought it was a great talk.
Good. Yeah, it's a tricky business, anonymity.